Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 11th physics, get more than 95% marks series. Today's lesson is system of particles and rotational motion. Chapter 7, NCERT line by line, part 7. We request you to subscribe our channel if you have not done yet. Please click on the like button and share our videos to your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us so that you will not miss any of our important videos and notifications. Let us begin today's class. Today we'll start with 7.11, that is kinematics of rotational motion about fixed axis. We have already indicated the analogy between the rotational motion and translational motion, that is v is equal to omega r. For example, the angular velocity omega plays the same role in the rotation as the linear velocity v in the translation. We wish to take this analogy further. In doing so, we shall restrict the discussion only to rotation about fixed axis. This case of motion involves only one degree of freedom, that is, needs only one independent variable to describe the motion. This is translation corresponds to linear motion. This section is limited only to kinematics. We shall turn to dynamics in later section. We recall that for specifying the angular displacement of rotating body, we take any particle like P, figure 7.33 of the body. Its angular displacement is theta in the plane it moves in. The angular displacement of the whole body, theta, is measured from a fixed direction in the plane of motion of P, which we take to be x dash, axis chosen parallel to x-axis. Note, we as shown, the axis of rotation is z-axis and the plane of motion of the particle is xy plane. Then from figure 7.33 shows that theta 0, the angular displacement at t is equal to 0. We also recall the angular velocity is the time rate of change of angular displacement. So omega is equal to d theta by dt. Note, since the axis of rotation is fixed, there is no need to treat angular velocity as vector. Further, angular acceleration alpha is equal to rate of change of angular velocity, that is d omega by dt. The kinematical quantities in rotational motion, angular displacement theta, angular velocity omega, and angular acceleration alpha, respectively, corresponds to the kinematic quantities in linear motion: displacement x, velocity v, and acceleration a. So this angular displacement represents as linear displacement x, angular velocity omega in linear velocity is v, and angular acceleration alpha and linear acceleration is a. We know the kinematical equation of linear motion with the uniform, that is constant acceleration. V is equal to v naught a plus at, so x is equal to x naught plus u naught t plus half at square, and v square is equal to v naught square plus 2as, where x0 or x naught is initial displacement, v0 or v naught is initial velocity, and the word initial refers to the values of the quantity at t is equal to 0. The corresponding kinematic equation for rotational motion with the uniform angular accelerations are omega is equal to omega naught plus alpha t, theta is equal to theta naught plus omega naught t plus half alpha t square, and omega square is equal to omega naught square plus 2 alpha theta minus theta naught, where theta naught the initial angular displacement of the rotating body and uh, omega naught the initial angular velocity of the body. So let us see few solved examples. 7.13 obtain equation 7.38 from the first principle. The angular acceleration of is uniform, therefore we can write d omega by dt is equal to alpha, that is constant. Integrating the equation, so we can write omega is equal to integration of alpha dt plus c, constant integration constant, where c is the integration constant. So you can write alpha dt's integration is alpha t, and c is a constant, it will remain as it is. So omega is equal to alpha t plus c. At t is equal to 0, omega is equal to omega naught. So we can write from equation 1 we get t is equal to 0. So put the value t is equal to 0 in equation 1. So we get omega is equal to c is equal to omega naught. If we put t is equal to 0, so if we put t is equal to 0, we get omega is equal to omega naught, and alpha into delta t, that is 0. This becomes 0. What is left? Only c. So omega naught is equal to c. So here putting the values, omega is equal to alpha t plus, instead of c we have put omega naught. With the definition of omega is equal to d theta by dt, we may integrate equation 7.38 to get 7.39. This derivation and the derivation of equation 7.40 is left as an exercise. So let us solve the next sum. The angular speed of a motor wheel is increased by 200 rotation per meter. RPM is rotation per meter, per minute, rotation per minute, to 3120 rotation per minute in 16 seconds. What is its angular acceleration? Assuming the acceleration is to be uniform. Second, how many revolution does the engine makes during this time? We shall use omega is equal to omega naught plus alpha t. Omega naught is equal to initial angular speed in radian per second, which is equal to 2 pi angular speed in revolution per second, that is 2 pi angular speed in revolution per minute, that is 60 second. We have converted into 60 second, and ultimately we got 2 pi by 1200 upon 60 radian per second, that is upon solving we get 40 pi radian per second. Similarly, omega is the final angular speed of radian per second, that is 2 pi multiplied by 3120 upon 60 radian per second. Upon solving we get 104 radian per second, 104 pi radian per second. Angular acceleration alpha is equal to omega minus omega naught t. So this can be found, why we have written this? This can be found in this way: omega naught plus alpha t. So omega minus omega naught is equal to alpha t. So omega minus omega naught upon L upon t, which is equal to alpha. So from here we got alpha t. Or we can also write this equation: rate of change of velocity is known as acceleration. Similarly, rate of change of angular velocity is known as angular acceleration. In that way, change of acceleration is this, and rate just divide by time, it gives the rate. So the angular acceleration of the engine is 5 pi radian per second square, and the second part, the angular displacement in time t, is given by theta is equal to omega naught t plus half alpha t square. Putting all the values, we get this 1152 pi radian. Number of revolution is equal to this distance, total distance, upon 2 pi. Why 2 pi? Because one revolution, it covers 2 pi, that is 360 degree. So it covers 2 pi here. So number of revolution, if we want to find, divide by 2 pi, and we get this value, number of revolution. Now we'll discuss dynamics of a rotational motion about fixed axis. Table 7.2 lists quantities associated with the linear motion and their analogues in rotational motion. So let us see table 7.2. So in linear motion, what is displacement x? In angular motion, the same is represented by angular displacement theta. In linear motion, velocity is equal to dx by dt, v is equal to dx by dt. In angular motion, angular velocity omega is equal to d theta by dt. In linear motion, acceleration a is equal to dy by dt. In angular motion, angular acceleration alpha is equal to d omega by dt. In linear motion, mass is equal to m. In angular motion, mass is equal to moment of inertia is equal to I. It is same as that of mass in linear motion. In linear motion, F is equal to ma. In angular motion, F represented by torque, and torque tau is equal to I alpha. In linear motion, work done W is equal to F ds. In angular motion, work done W is equal to tau d theta. Because F is represented by torque, so instead of F we have written tau. Displacement is represented by distance is represented by ds. So in angular motion, distance is represented by d theta. Kinetic energy K is equal to half mv square in linear motion. In rotational motion about a fixed axis, kinetic energy K is equal to I omega square by 2. In linear motion, power P is equal to Fv. In angular motion, power P is equal to tau omega. In linear momentum, P is equal to mv. In angular momentum, L is equal to I omega. So this is all about the table 7.2. Now let us go back and check. So table 7.2 lists quantities associated with the linear motion and their analogues in the rotational motion. We have already compared kinematics of the two motion. Also, we know the rotational motion Moment of inertia and torque plays the same role as mass and force respectively in the linear motion. Given this, we should be able to guess what the other analogs indicate integrated in the table are. For example, we know that the linear motion work done is given by FDS. In rotational motion about a fixed axis, it should be tau d theta. Since we already know the correspondence, dx is represented by d theta in angular motion. F is represented by uh, F is equal to tau in angular motion. It is, however, necessary that these correspondences are established on sound dynamics consideration. This is what we turn to. Before being, we note a that simplification that arises in the case of rotational motion about fixed axis. Since the axis is fixed, only those components of torque which are along the direction of a fixed axis need to be considered in our discussion. Only these components can cause the body of rotation about the axis. A component of torque perpendicular to the axis of rotation will tend to turn the axis from its position. We specifically assume that there will arise necessary forces of constraints to cancel the effect of the perpendicular components of external torque so that the fixed position of the axis will be maintained. The perpendicular components of the torque therefore need not be taken into account. This means that our calculation of torque on a rigid body, we need to consider those forces that lie in the planes perpendicular to the axis. Forces which are parallel to the axis will give torque perpendicular to the axis and need not be taken into account. Second, we need to consider only those components of position vector which are perpendicular to the axis. Components of position vector along the axis will result torque perpendicular to the axis need to not taken into consideration or taken into account. Work done by torque. In figure 7.34 shows the cross-section of a rigid body rotating about the fixed axis which is taken as z-axis perpendicular to the plane of the page. See figure 7.33. As said above, we need to consider only the forces which lie in the perpendicular in planes perpendicular to the axis. Let F1 be one such typical force acting as shown in the particle of the body at point Pi at point P1 with its line of action in the plane perpendicular to the axis. For convenience, we call this to be x dash y dash plane coincide coincident with the plane of the page. The particle at P1 describes the circular path of radius r1 with the center C on the axis Cp1 is equal to r1. In time delta t, the point moves to the position P1 dash. The displacement of the particle ds1 therefore has magnitude ds1 is equal to r1 d theta and direction tangential to P1 to the circular path as shown. Here d theta is the angular displacement of the particle. D theta is equal to angle P1C P1 dash, the work done by the force on the particle is dw1 is equal to f1 ds1 is equal to f1 ds1 cos phi 1 is equal to f1 r d theta sine alpha 1, where phi 1 is the angle between force and the tangent. So let us see the figure here. So this is angle is theta, a small angle, small displacement. You can say this one is d theta, and a small arc that is ds1, which is making an angle alpha with the radius here, with the r1 here with the dotted line, and it makes phi 1 with the force. So we can write here, we know work done is equal to force into displacement. So dwi is equal to fi dot ds. We can write fi dot product as fs cos theta. So here fi dsi cos phi I, which can be written as fi r d theta. So mm, instead of ds, we can write r1 d theta. Why instead of ds? So say this is small arc. So this is ds, this is d theta, this is r. So arc is equal to ds. So we can write for very small arc ds is equal to r d theta. So here we have put the value of ds here. So f1 fi r r1 d theta and sine alpha I. So where phi is the angle between force and the tangent, at P1, and alpha is the angle between the force F1 and the radius OP. Therefore, phi 1 plus alpha 1 is equal to 90 degree. Therefore, cos phi 1 we can write cos 90 degree minus alpha 1, that is sine alpha 1 from trigonometrical law. So we got this. Now let us move forward. The torque due to Fi about the origin OP1 is into F1. Now OP1 we can write OC plus OP1. So we have done in the previous lessons. They are referring to the old image which has done 2 or 3 class before. So since OC is along the axis, the torque resulting from it is executed from our consideration. The effective torque due to F1 is tau 1 is equal to Cp F1. It is directed along the rotation and has magnitude tau 1 is equal to R1 F1 sine alpha. Therefore, dw1 is equal to tau 1 d theta. If there is more than one forces acting on the body, the work done by all of them can be added to give the total work done on the body, denoting the magnitude of the torque due to the different forces tau 1, tau 2, tau 3, etc. dw is equal to tau 1 plus tau 2 plus dot 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 d theta. Remember the forces giving rise to the torque act on the different particles, but the angular displacement d theta is the same for all the particles. Since all the torques considered are parallel to the fixed axis, the magnitude of tau of the total torque is just the algebraic sum of the magnitude of the torques, that is tau is equal to tau 1 plus tau 2 plus dot dot dot. We therefore have dw is equal to tau d theta. So main thing is this, that how linear momentums and the physical quantities in linear moments are representing or changing in angular momentums. That's it. So this expression gives the work done by the total external torque tau, which acts on a body rotating about a fixed axis. Its similarity with the corresponding expression dw is equal to f ds for linear translational motion is obvious. Now, dividing both the side of the equation 7.41 by dt, it gives p is equal to dw by dt and tau d theta by dt. So d theta by dt we can write omega. So tau omega. So power is equal to tau omega. We have derived this. In 41 we have derived tau d theta. Dow is equal to tau d theta. This is the instantaneous power. Comparing this equation, comparing with this expression with the power, in this case, rotational motion about the fixed axis with the expression of power in linear motion is Fv. In perfectly rigid body, there is no internal motion. The work done by the external torque is therefore not dissipated and goes on to increase the kinetic energy of the body. The rate at which the work done on the body is given by the equation 7.42. This is equated to the rate of which kinetic energy increases. The rate of increase of kinetic energy is represented by d I omega square upon 2 dt is equal to omega I omega square can be written as differentiate as I 2 omega d omega by dt. So we can write, we assume the moment of inertia does not change with time. This means that mass of the body does not change, the body remains rigid, and also the axis do not change in this position with respect to the body. So alpha is equal to d omega by dt. So we can write d omega by dt as alpha. This is alpha, and this 2 and 2 gets cancelled. So ultimately we got I omega alpha. Equating the rate of work done and to increase the kinetic energy, tau omega is equal to I omega alpha. So tau is equal to I alpha. So we have derived this equation. Equation 7.43 is same as that of Newton's second law of linear motion expression F is equal to ma. So tau is represented by F, m is I, and a is alpha. Just as the force produce acceleration, torque produce the angular acceleration in the body. The angular acceleration is directly proportional to the applied torque and inversely proportional to the moment of inertia of the body. So this is an important part. The angular acceleration is directly proportional to the torque and inversely proportional to the moment of inertia of the body. Equation 7.43 can be called Newton's second law of motion in rotation for rotation about a fixed axis. Let us see few of the solved examples. Example 7.15. A cord of negligible mass is wound around a rim to fly a wheel of mass 20 kg and radius 20 centimeter. A steady pull of 25 Newton is applied on the cord shown in figure 7.35. The flywheel is mounted on the horizontal axis with the frictionless bearing. Compute the angular acceleration of the wheel. Find the work done by the pull when 2 meter of the cord is unwound. Find also the kinetic energy of the wheel at this point. Assume that the wheel starts from rest. Compare answer to the part B and C. Now, in the figure, it is given F is equal to 25 Newton here, mass is equal to 20 kg, and radius is equal to 20 centimeter. So, first, what we'll do, we'll find out the tau. So, I alpha torque is equal to Fr, that is 25 multiplied by 0.2, which is equal to 5 Newton meter. Now, moment of inertia of the flywheel about its axis is mr square by 2. Putting the values, we get 0.4 kg meter square. Alpha is equal to angular acceleration. Therefore, tau is equal to angular acceleration. So I upon alpha. So I upon alpha is equal to um, no alpha is equal to we got tau is equal to I alpha. Therefore, alpha is equal to tau by I. So we put the value of tau 5 Newton meter and alpha zero point 0.4 kg I as 0.4 kg meter square. Therefore, we got the value of the alpha. Now, work done by pulling the unwind 2 meter of cord, that is work done is equal to normal. If you have to remember, work done is equal to force into dis displacement. So here work done will be equal to force can be represented by tau and displacement can be represented by d theta, tau d theta. So here d theta is 20. So in this case FDS, so F is 25 Newton and ds is 2 meter, that is 2 meter. So this is 50 joule. Let omega be the final angular velocity and kinetic energy gained is equal to half I omega square. Since you have to remember these formulas, so since the will start from rest, now omega square is equal to omega naught square plus plus 2 alpha theta. So omega naught is 0 The angular moment, displacement theta is equal to length of the unwound string per radius of the wheel, that is 2 meter upon 0.2 meter, that is 10 radian. So omega square, put the values of omega square and other values. So we get omega square is equal to this, and kinetic energy is equal to half I omega square, and put the values of I and omega square. We get 50 joule. The answer are same, that is the kinetic energy gained by the wheel is equal to work done by the force. There is no energy loss due to friction. Angular momentum in case of rotation about fixed axis. We have studied in section 7.7 the angular momentum of a system of particle. We already know from there that the time rate of total angular momentum of a system of particle about the point in is equal to the external torque of the system taken about the same point. When the total external torque is zero, the total angular momentum of the system is conserved. If now we wish to study the angular momentum in a special case of rotation about the fixed axis, the general expression for the total angular momentum of the system L is equal to sigma I is equal to 1 to till n Ri pi. This is equation 7.25b. We first consider the angular momentum of a typical particle of rotating rigid body. We then sum up the contribution of individual particle to get L as a whole body. The typical article L is equal to R multiplied by T as seen in the last section. R is equal to OP is equal to OC plus CP. So we have already done it in the previous classes, this relation with P is equal to MV. So I is equal to OC multiplied by MV plus CP multiplied by MV. The magnitude of linear velocity V of a particle at P is given by V is equal to omega r perpendicular, where r perpendicular is the length of the CP or the perpendicular distance of P from the axis of rotation. For the V is the tangential at P to the circle which the particle describes. Using the right hand rule, one can check that Cp into V is parallel to the fixed axis. The unit vector along the fixed axis chosen as z-axis is r perpendicular, that is Cp multiplied by mv is equal to r perpendicular mv, r which is equal to m r square perpendicular omega square. Now similarly we can check OC into V is perpendicular to the fixed axis. Let us denote the part of L along the fixed axis, that is z axis, by Iz. Therefore Iz is equal to Cp into Mv, which is equal to mr perpendicular square omega square, and L is equal to uh, Iz, I is equal to Iz plus Oc into Mv. We note that Iz is parallel to the fixed axis, but I is not. In general, the particle, the angular momentum L, this is L, angular momentum L is not along the axis of rotation. For particle, L and omega are not necessarily parallel. Compared with the corresponding fact in translation. In translation, for a particle P and V are always parallel to each other. For computing the total angular momentum, of a whole rigid body, we add up the contribution of each particle of the body. Then, thus, L is equal to sigma Li, which minus sigma Lv plus sigma OCI plus MIVI. We denote Li, L perpendicular and Lx, Lz, the components of L respectively perpendicular to z-axis along z-axis. L perpendicular is equal to sigma OCI plus MIVI, where MIVI are respectively the mass of the velocity of ith particle and Ci is the center of circle described by the particle. So Lz is equal to sigma L Liz is equal to sigma I mi r I square omega square. Lz is equal to I omega square. The last step from the follow the since the perpendicular distance of ith particle from the axis, that is Ri, by the definition of moment of inertia, the body about the axis of rotation I is equal to MIRI square. So the rigid, so L is equal to Lz plus L perpendicular. The rigid body which we have mainly considered in this chapter are symmetrically about the axis of rotation. Symmetric about the axis of rotation. That is, axis of rotation is one of the symmetry axis, one of their symmetry axis. For such bodies, we have OC1 for particles which has the velocity vi, v1 or vi. There, there is another particle of velocity minus vi located dramatically opposite to the circle with the center Ci described by the particle. Together, such pair will contribute 0 to L perpendicular. As the result of symmetric bodies, L perpendicular is 0, and hence L is equal to Lx is equal to I omega I omega square. For the body which is not symmetry about the axis of rotation, L is not equal to Lx and L does not lie on the axis of rotation. Referring to the table 7.1, can you get can you tell which case L and Lx will not apply? Let us differentiate equation 7.44b. Since lambda is a constant, fixed constant vector, we get del d Lx by dt is equal to di omega upon dt lambda. Now, equation 7.28b can be states that dl by dt is equal to tau. As we have seen in the last section, only those components of the external torque which are along the axis of rotation need to be taken into account when the discussion of rotation about the fixed axis. This means that we take account to take uh, tau lambda. Since L is equal to Lz plus L perpendicular, the direction of Lx vector lambda is fixed, and it follows for rotation about the fixed axis. Lx upon dlx upon dt is equal to tau lambda and dl1 by dt is equal to 0. Thus, the rotation about a fixed body, the component of angular momentum perpendicular to the fixed axis are constant, as Lz is equal to I omega lambda square. We get from the equation 7.45a. Differentiating this, we get differentiation of I omega and tau, since lambda is a constant. If the moment of inertia I does not change with the time, d I omega upon dt is equal to I d omega by dt is equal to I alpha. And we get from equation 7.45c and tau is equal to I alpha. We have already derived this equation using the work kinetic energy route. Let us now see conservation of angular momentum. Conservation of angular momentum means angular momentum is conserved, and so mathematically we can write L is equal to I omega is equal to constant. It doesn't change. So there are a few examples, a circus abort and a driver take advantage of this principle. Also, skaters and classical Indian or Western dance performing on the toes of one foot also takes the advantage of this principle. Now, rolling motion. So, a different type of motion is rolling motion. So, uh, when the object starts rolling, then the linear motion converts to angular angular motion. So we'll derive the expression for the kinetic energy of rolling motion. So for example, so rolling the rolling caused by the angular motion as well as the translation motion. So kinetic energy K is equal to total kinetic energy of the particle is K dash and half mv square. And upon solving this, we can write K is equal to half I omega square and half mv square. Half I omega square is for rotational motion and half mv square is for uh, linear motion. Uh, Substituting the value of I is equal to mk square, where k is the corresponding radius of gyration of the body, and vcm is equal to r omega, we get k is equal to half k mk square vcm square upon r square plus half mvcm square. K is equal to half mvcm square bracket 1 upon k square by r square. This is the expression for total kinetic energy of a rolling body. Now let us do a problem example. Three bodies, a ring, a solid cylinder and a solid sphere roll down same inclined plane without slipping. They start from rest. The radii of the body are identical. Which body reaches the ground with maximum velocity? We assume the conservation of energy of a rolling body. There are no loss of energy, and due to friction, the potential uh, energy lost by the body rolling down the inclined plane mgh must be therefore equal to the kinetic energy gained. Since the body starts with rest, kinetic energy gained in is equal to the final kinetic energy of the body. So final kinetic energy is body of the body is equal to half mv square bracket 1 plus k square by r square. It is already given, where v is the final velocity of the center of mass of the body, equating K and MGH. Now, uh, in the figure, it is clear that theta is the angle of inclination, this is the h is the height, and r is the radius. So, what we can write is mgh is the potential energy. What is potential energy? Say this is the ground and you are holding a mass here of m at a height, say h, then energy is stored. And what type of energy is stored here? Potential energy. And what will be the value of potential energy here? mgh is the value. So we have, and as soon as we throw this, then it converts, the potential energy converts to kinetic energy. So mgh is equal to half mv square bracket 1 plus k square by r square. So v square is equal to this much upon calculation. Note, is independent of mass and rigid body. This is independent of mass. Nowhere we can see mass. For a ring, k square is equal to r square. So put the value, v ring is equal to under root 2 gh upon 1 plus 1, and ultimately after solving we get root root 2 square root gh. For a solid cylinder, h is equal to r square by 2. So putting these values in the equation, so we get v disk is equal to under root 2 gh 1 plus half, that is 3 by 2 upon solving 4 gh by 3. For a solid sphere, k square is equal to 2r square 5. So b sphere is equal to under root 2 gh plus upon 1 plus 2 by 5, that is 10 gh by 7. From the result obtained, it is clear that among the three bodies, has the greatest. Sphere has the greatest, and the ring has the least velocity of the center of mass at the bottom of the inclined plane. Suppose the body have same mass with which the body is has the greatest rotational kinetic energy while reaching the bottom of the inclined plane. So this is the main thing, that which has, if we roll ring, cylinder and sphere, then which has the uh, more which is more kinetic energy. So we have written this. So which have more velocity. So it is proven that the sphere has the greatest velocity and ring has the least velocity. And this is the end of the chapter. Therefore, before we end the class, we request you to subscribe our channel if you have not done yet. Please like our videos and share these videos among your friends so that they can be benefited about this. Thank you for giving time to watch our videos, and thank you for supporting us. Thank you very much.